Hello, I would like to welcome you to lecture 23 of ENG3N03. I will discuss in this lecture three types of flip-flops, and the flip-flops are sequential circuits that we can use them as memory elements. They are able to store data in them, so you can store data in these memory elements. They have a memory. They are not like combinational circuits that do not have memory. They depend just on the instantaneous value of the input. So I will discuss some of these flip-flops, and there are other types of flip-flops you can read about, but these ones will hopefully give you the basic idea of how these circuits work. So I have seen in previous lectures what's a combinational logic circuit. A combinational logic circuit is really a logical circuit whose output depend on the current values of the input. If the values of the input change, the value of the output will automatically change. It does not keep any memory. While sequential circuits, they use some sort of feedback from the output to the input to create a memory element. So once we store, say, 1 in a bit, this bit can be kept even if the input changes. And then we can, of course, store new values and so on. And they are very useful for creating registers and memory elements. The first RS flip-flop the first flip-flop I'll talk about is called the RS flip-flop, and it is shown here. You can see it is simply two NAND gates, and we create some feedback from the output to the first NAND gate to the input to the second NAND gate, and from the output to the second NAND gate to the input to the first NAND gate. They call it RS flip-flop, meaning reset and set. R for reset and S for set. So, and the one I'm showing you here is called an active low flip-flop, and you'll understand why this is the case in a second. If you put 1 and 1 at both inputs, if you put logic 1 here and logic 1 here, this result in a do not change condition. This is simply the resting condition, meaning if Q is 1 and Q bar is 0, and by the way, Q and Q bar are always opposite to one another. If this is 1, this is 0. If this is 0, this is 1. If this is 1 here and this is 0 here, if you put 1 and 1, this will result in no change in the value. They will still be 1 and 0 or 0 and 1. It doesn't matter. Whatever in the memory will be in the memory. So reset and set is the value that we should put if you do not want to make any changes. Now, if you put set equal to 0 and reset equal to 1, and as I said, this is an active low. Active low meaning that when I put set equal to 0, this means I want to set the flip-flop. If you put this equal to 0 and this S equal to 0 and the R equal to 1, this will result in Q becoming 1 and Q bar becoming 0. Okay, so let's see how this works. If you put here a 1 at the input, if you put 1 here at the input, okay, and you put 0 here, okay, so because this is 0, and this is an AND, you get 1 here. Okay. Actually, so let's backtrack that again. Actually, I would like to consider the case of 0 and 1, not 1 and 0. So let me erase this one first here. Let me erase this one. I'm doing it the other way around. So the first case we want to consider is 0 and 1, and the reason for that is an active low. 0 and 1 is an active low RS flip-flop. Now, if I put 0 here and 1 here, if I put 0 here, this is an AND, so this Q becomes 1, so you get 1 here at the output, okay? And if this is 1 here at the output, and this is 1, then the output here must become 0, because this is an AND, okay? So here, this is your beer output, this is a set condition. Set condition meaning it's an active low, so when you put set equal to 0, the Q will be equal to 1, okay? So 0 and 1 will result in a set condition which is 1 and 0. Q is 1 and Q bar is 0. Now, if you have already 1 and 0 at the output and then you make set and reset both equal to 1, this will result in no change of the output. 1 and 0 will still be kept there. Now, let's consider another case which is a reset case. So I will just erase what I have here, and then I will put the opposite condition. The opposite condition is that I have 1 for set and 0 for reset. And remember, when I put 0, 0 means it's active. So indeed, I want to reset this flip-flop. I would like to make Q equal to 0. Now, because this is 0, the output from the NAND will be equal to 1, regardless of anything else. Okay? And because Q bar now is 1, and you have S is equal to 1, the output from the NAND will be equal to 0. So indeed, the RS flip-flop has been reset. Okay? Now the last condition or the last state, when you have the set and reset both equal to 0, which means you want them both to become active, and this is forbidden. This is a case that should not happen, because this will result in a conflicting conditions in your logic gates. Because if you have 0 and 0, this means that this will become 1 and 1, okay? But if you have 1 and 0, this will not be consistent with the circuit. You cannot have them both like that, okay? So if the condition 0 and 0 will result in always 1 and 1 here at the output, but this will not be consistent, or it's not a forbidden condition, as a forbidden condition for us in this circuit. So for this circuit, we have to use it in 3 cases. The first one is set. S is 0, R and 1 will result in Q equal to 1, Q bar equal to 0. The second one is reset. S is 1, R is 0 will result in Q equal to 0 and Q bar equal to 1. The third state is don't change, keep it as it is. And this one, set is equal to 1, R is equal to 1, then whatever is at the output will still be the same, will not be unchanged. If you have 0 and 1 or 1 and 0 will be the same. So this is the circuit symbol for an RS, for an active low RS flip-flop. How do you know it's active low? By these 2 bubbles here that you have at this case. So remember, we do not allow the reset equal to 0 case, because one of them has to be on, because it's an active low. So either you are resetting or you are resetting. You are resetting or resetting. You cannot be doing both. So both of them, this condition is forbidden here. Okay, let's draw the truth table for this RS flip-flop, and as you can see here, we take the current state of the RS flip-flop as an input. It is not like combinational logic circuits where the output will depend only on the inputs. The output depends on the inputs and the current state. So when you have 0 and 0, this is a forbidden state. This should not be allowed. 0, 1, this is a reset. So regardless of Qn, the output will always be 1. So the same thing will be repeated here. When you have 0 and 1, this is a set. When you have 0 and 1, this is a set. It's an active low. S is equal to 0, R is equal to 1. It's a set. The output will be equal to 1 regardless of Qn. This is why here you can see when you have 0 and 1 again, the output becomes 1 regardless of Qn. Now the second case, 1 and 0. 1 and 0, it's an active low, so 1 and 0 is meaning reset. The output becomes 0 regardless of Qn. The same thing is happening here again. You have 1 and 0. So this is meaning reset. So the output is 0 regardless of Qn. Okay? Again, 0 and 0 is forbidden. 1 and 1 means do not change. So 1 and 1, if you have 1 and 1 for the R and S inputs, and Qn was 1, Qn plus 1 will also be 1. If you have 1 and 1 and the current state was 0, the output will still be 0. It will not be changed. Okay, so this is the truth table of this RS flip-flop, and it shows you how the new state of the output depends on the current state and the inputs that we have. And this, as I said, is an active low flip-flop. You can draw a similar truth table or build a similar truth table for an active high RS flip-flop. Okay, we can build a Carnot map as we explained before in the lectures on how to. This will help us simplify the implementation of this RS flip-flop. So I brought here all the possible combinations for the inputs RS 0, 0, 0, 1, 1, 1, and 1, 0, and both 0 and 1. As we agreed, when you have 0 and 1, the flip-flop will be set, so you get here 1 and 1. Okay, and here you should understand this Carnot map shows Qn plus 1, the new state, for using the current input, the input and the current state. So 0 and 1 means set the flip-flop, so the output is 1. 1 and 0 means reset the flip-flop. I'm not showing you the zeros here, but these are all zeros. 1 and 1 means do not change. So if you have 0, you get 0. If you have 1, you get 1. Okay? 0 and 0 is a forbidden state. Forbidden means that it will, when I design such a logic circuit, I'm not going to allow this situation to appear. So I can take it as a do not care. Do not care means it can be, I can take it in my Carnot map as either 0 or 1. So you can see if I make them equal to 1, this will help me lump or group these 4 together to create a much simpler logic table, or much simpler implementation of my logic circuit. This is why I'll take them as 1 and 1. So this is telling me that when you have S is equal to 0, regardless of R and regardless of Q, I will get 1. When I group these two together, this is simply telling me when Qn is equal to 1, the current state is 1, and the R is equal to 1 is always, I will also get 1. So these, when I write the logical expression for these two groups, the R S bar, S is equal to 0 in these 4, and the R Qn equal to 1, and R is equal to 1, so R Qn. So I can put it here as sum of products as we explained earlier. We can, of course, the problem with an RS flip-flop, I would like in many applications to get the memory set or reset, or to load new data into registers only with clock, with a computer clock. And this is what we have in all our devices. There is some clock that determines that determines the order of execution of commands in the microprocessor, inside our cell phones or inside our computers and so on. So this is one way of doing this. This is our RS flip-flop. This is an active low flip-flop, as I explained earlier. So when you put S equal to 0, you get 1. 0, so 0 and 1. 0 and 1 will create 1 and 0. If you put 1 and 0, will create 0 and 1. If you put 1 and 1, do not change. 0 and 0 is forbidden. Okay? So what we can do, we can create take two NAND gates again, and then we have the clock as one of the inputs. So when the clock is low, when you have low here, this means that two NANDs will create 1. 1 and 1 here meaning do not change. So whatever is stored in this memory element, whatever is stored in this flip-flop will be the same. When I make the clock equal to 1, okay, so if set is equal to 1, it will be transformed to 0 at the output, meaning set the flip-flop. When you have 1 and 0, it will create 1 and 0 at the output. Now when if this one is 0 and 1, if you have 0 and 1, 0 and 1 will be transformed, if clock is high, to 1 and 0, meaning that the output will be 0 and 1. So this one here is really an implementation of an active high RS flip-flop, meaning that when you put set equal to 0, when S is equal to 1 and the R is equal to 0, you are actually setting the flip-flop. Q will be equal to 1, Q bar will be equal to 0. When set is equal to 0 and R is equal to 1, you are resetting the flip-flop. The output Q bar will be equal to 0 and 1. Okay? So you can see everything here will be dependent on the clock going high. So you can have your clock, and at the moments when the clock is high, these are the only moments where you can have a change in the value of the flip-flop. When the clock goes low, the output of the two NANDs will be 1, resulting in a do not state condition, not a change condition. So meaning that whatever is in the memory will be stored in this memory. A second type of flip-flop is a JK flip-flop, and the JK flip-flop is really a modification of the RS flip-flop by eliminating the forbidden case. So J will play the role of the set, K will play the role of the reset, and everything else will follow exactly the same way. And here I'm assuming that for change to happen, we must have a clock, and this clock must be 1. So the clock, when the clock level is 1, this is what enables the change in my JK flip-flop. And I'm showing you here two different cases. This is an active high flip-flop, JK flip-flop. This is an active low JK flip-flop, and you can see these bubbles are telling you that the inputs are inverted. So in the set condition, if you put J equal to 1, K equal to 0, and if the clock is 1, the output will be set equal to 1 regardless of the current state. So the Q will be 1 and Q bar will be 0. In the reset condition, you put j equal to 0 and k equal to 1. In that case, the output k will be 0 and q bar will be 1. Okay, so you can see here the next state, and here I'm not showing q bar, I'm only showing the new state of q. This will be reset. Now, as in the previous case, this is, as I said, this is an active high. This one here is an active high. If I put 0 and 0 means do not change. Whatever is there will remain there. So the new value of the output will be equal to the previous value of the output before you apply this input. The last condition, which was forbidden, which was 1 and 1, 1 and 1 for an active high. Now this case will become a toggle condition. So if Qn was 0, it becomes 1. If Qn was 1, it becomes 0. So the new state of the output is the complement of the, or the negation, logical negation of the input, of the current state, sorry. So Qn plus 1 will be the negation of the current state. The same thing is happening for an active low. Active low means if you want to set the flip-flop, put j equal to 0 and k equal to 1, then this will create for you 1 and 0 at the output. If you want to reset it, put j equal to 1 and q is equal to 0, so this means this is reset. This will create 0 and 1 at the output. No change is simply, in this case, 1 and 1. No change is 1 and 1. Because 1 and 1, after you invert them with these bubbles, becomes 0 and 0, means Qn plus 1 will be equal to Qn. Toggle is when you both of them are equal to zeros. And in that case, the new state of the output will be equal to the negation of the previous state. Okay, as an example, let's try to build a chronomap of the implementation of an active low JK flip-flop. So would like to know, and I didn't talk any about the clock here, so I'm assuming it's not gonna be clocked, and I will show you one way to make it edge triggered or to make it controlled in a certain way so that we don't have a racing happening in our flip-flop. I will explain this in a second. So now let's try to build a chronomap. The way for building a chronomap is simply to build a truth table, try to group your variables, logical variables, in the groups of 1, 2, or 4, and then put all the information on your truth table, and then try to create groups, and then you try to write more simplified logical expressions. So let's do that. Let's now do that for this GK flip-flop. Okay, so this is an active low GK flip-flop. So when you put 0 and 1, 0 and 1, 0 and 1, this may simply means set. So the new output for Q will be 1 regardless of the current state. So I'm showing you here that these are the two inputs. This is the current state and this is the new state. So these two here, 0 and 1, means set. So the output is 1 regardless of the current state. When you put 1 and 0, 1 and 0 means reset regardless of Qn. Then the new output will be 0. When you put 1 and 1, remember this is an active low, so 1 and 1 means do not change. So here 1 and 1 and 1 and 1. If Qn is 0, Qn plus 1 will be 0. So if the current state of the output was 1, and then you put 1 and 1, it will still be 1. If the current state of the output is 0 and you put 1 and 1, it will still be 0. Okay? The last change which differentiate the JK flip-flop from the RS flip-flop is a 0-0 state. 0-0 state when both JK are 0. This was forbidden before in RS flip-flops. This will result now in a toggle. So if the current output was 0, the new output will be 1. If the current output was 1, the new output will be 0. So now this is a whole table. I have 8 possible inputs, okay, and I'm showing you the output for all of them. Now we convert this into a chronomap. I'm putting JK in the column case, and I'm putting Qn in the row case, and we take all the ones here, we map them to this map, and then we try to lump them together. So one possible grouping here, and this probably will be the one that creates the least number of groups, is to group these two together and group these two together. So you can see for this one here, this is simply telling you if Qn is 0, logic 0, and JK is logic 0, then you're going to get 1. So this group here is simply J bar, Qn bar. While for this one here, is telling you as long as the current state is 1 and k is 1, you are going to get 1. So this one here is simply equal to QNK. So this is the expression for the output of the JK flip-flop. Qn plus 1, the new state of this flip-flop will be Qn bar J bar, so it depends on the current state, plus Qnk. This depends on the current state and of the two inputs J and K. The previous expression I explained to you is simply had two terms. The first one is QNK, so this what implement this expression, and the second one is Qn bar J bar, and this term here is what, or this logic circuit, these logic gates are what implement this expression. And here I'm doing a sum of product. So Qn is equal to Qn plus 1, the new value of Qn is equal to Qn bar J bar plus Qnk. Now this implementation has a problem. What is the problem here? If you apply certain input and the output will change, you are feeding the input again. You are feeding the output again to the input. So this may result in even further changing of the state. This is called racing. In order for this racing to be eliminated, you have to make the duration at which JK change from their do not change situation has to be short. So in other words, the periods where J and K are either in the set, reset, or toggle will have to be extremely short. Otherwise, you create a change, and this change is fed back again to create another change. So the duration for these two, for the JK, has to be extremely small. And you will see later when we talk about delays how to create a delay in order to use it to create such very short pulses at the input. And these short pulses will allow you to set, reset, or toggle, but they have to be very short, a very short deviation from the do not change state. Okay, another type of flip-flop we can talk about is the toggle flip-flop. And toggle flip-flop, every time there is a rising edge of your clock or there's a falling edge, the output will toggle. So if you had 1 here, it becomes 0. If you have 0, it becomes 1. And this is very useful actually for creating counters. Binary counters can be created by cascading a number of these toggle flip-flops. You can create binary counters because each one of these counters really divide by 2. Because if this one has a certain frequency, maybe you can try to do this one for you. If you have a certain frequency here at the input, okay, but you get toggling at every rising edge, then the output will look something like this. Maybe here it was 1, and then with this rising edge it will go to 0. And then with this rising edge again it will go to 1, and so on. So you see your output frequency here is 1/2 the input frequency. So this circuit effectively divides the frequency of your square wave by 1/2. And if you cascade another one, then we are dividing by 4. Another one we divide by 8. And this is why these toggle flip-flops are very useful in creating binary counters. Okay, as an example, let's use Carnot maps to implement edge-triggered T flip-flops. How can we do that in T flip-flops? I explained so far how to use level-triggered. Edge-triggered is not really that different. We would like to see whenever there is a rising edge or a falling edge that we are going to create a very short duration pulse. We use it to change the state of the flip-flop. So how do I create a pulse, a very short pulse at the rising edge? This is one way of implementing it. I have an AND gate, and the input is, both inputs are coming from the clock. So you can see here I'm having this input coming directly from the clock, and this one is the clock after it's being inverted. Now let's assume that the clock has been 0. If the clock has been 0, okay, then the input here is 0, this one here is 1, and the output is 0. So nothing is happening. Now at the rising edge, when you get a rising edge, So this one will change directly to 1. Okay, let me try to draw this one for you. This one here becomes 1. Maybe I should put it in a different color. So if I put this one here is 1, at exactly after the rising edge. But remember, this inverter will take some time to change its output from now. Before it had 0 input, so the output was 1. Now it has 1, but it will take some time before the output change to 0. So there will be a short duration of time where both inputs are 1. When you have such an input to the AND gate, it will create a very short pulse of duration, of a very short pulse of value of 5 volts or whatever, which we consider to be logic 1. And after that, you have 1 at the input. This becomes 0, and then the output goes immediately to 0 again. So this is a circuit to create a positive edge triggered circuit. You converted this rising edge to a very short pulse, very short pulse that you can use to trigger your flip-flop, to change the state of your flip-flop. Okay? Now, what about negative edge? If you have a negative edge, exactly the same thing. Let's assume that the input was high. If the input was 1, so this is 1 here, and this is 0. Maybe I should try to draw it for you. So if the input was 1, this is 1 here, and this is 0. But remember, this is inverted, so effectively to the input of this end, this is 0 and this is 1. It doesn't matter, the output in both of them is 0. So we have here 0. Okay, now we have a fallen edge. We have a fallen edge. It means that the output suddenly changed to 0. So now the condition has changed. So I can simply, this one here becomes 0. Okay, but this input will take some time because of the inverter. The inverter, all electronics gates have some delay. Your output becomes 0, but this will take some time for this output here to change from 0 to 1 as a result of the change that happened from 1 to 0 here. So there will be a very short duration of time where both inputs to this inverted AND gates are zeros. Okay, so when you have 0 and 0 here, they are inverted to become 1 and 1, and then you get this very narrow short pulse. After that, after this short duration of time, this input here becomes again 1, so this becomes 1, and then you end up getting 0 again at the output. So this circuit here I explained to you, this creates a very short pulse corresponding to a rising edge, while this one creates a very short pulse corresponding to a fallen edge. And then we can use these ones as input for our flip-flops, whether it's RS flip-flop or JK flip-flop or T flip-flop. There is another type called D flip-flop. We can make them all edge triggered through this way. Okay, for the toggle flip-flop, this is what we have. This is the current state, this is the toggle. Whenever the toggle is 1, the state will change from 0 to 1 or from 1 to 0. So this is when the toggle is 1. When the toggle is 0, there is no change. We still have the memory stored there, so the new state will be equal to the previous state. This is the truth table of an active high toggle flip-flop. Of course, I can put the form of chronomap. I have only two variables, the input T and the current state of the flip-flop. And you can see I cannot really do much grouping here. They are isolated. So this one here will give me 1 when T is 0 and Q is 1. So this is T bar Qn. While this one here will give me 1 when T is 1 and Qn is 0. So this one here is T Qn bar. So I have these two expressions, and then I can use them, of course, to implement my logic circuit. So this one is a possible implementation. So if you have 1 here, this will toggle the output. If the output is 0, it changed to 1. If the output is 1, change to 0. Of course, I cannot have 1 here for long, because if I have 1 here for long, this will toggle the output, resulting in a feedback to the input will result in more toggling. So remember, this input here will have to be very limited in time, and this can be edge triggered. Okay, it can be edge triggered, either positive edge triggered or negative edge triggered, so that by the time the delay happens in all these gates and the output is changing, the input will already disappear and there is no toggling signal anymore. It returns to its no change condition, and then the circuit can proceed.